Hello! In this session, we are going to talk about vectors. A vector is just something that has a magnitude and a direction. Now that might sound a little abstract, so let's look at some examples. So these are three common examples that we are quite familiar with. Displacement: if you move an object by a certain distance in a certain direction, that is a vector. Velocity is a vector. Velocity is the speed that something is moving at and its direction. And force, a force has a magnitude, how big is the force, and a force has direction. So all these three quantities are vectors. So in mathematics, we are interested in how to represent this vector and how to calculate with this vector. So to see how we would actually represent such a vector, let's look at an example. The simplest would be to look at displacement. So suppose there is a person, and this person is walking in a certain direction. Let's say he walks to the east. Alright, that's the east. And he walks for 100 meters. So that's a vector. That's his displacement. But we can represent this vector by saying that it is 100 meters and it is towards the east. So that's one way to represent a vector. And that's quite a lot of things to say. He walks for 100 meters and he's going towards the east. Now we can always make things simpler in some ways. For example, if I can, if we are talking about directions, as in north, south, east or west direction, we can think about bearings. We can refer the direction to, say, the north. Alright, so in this case, the north is up there. So the east is 90 degrees to the north. That means we have a bearing of 0, 9, 0 degrees. So that's how we represent a direction in geography. So 0, 9, 0 degrees would be the direction of this vector. So I can say that the magnitude is 100 meters and the direction is 0, 9, 0 degrees. So that's one way to represent a vector. Alright, as another example, I might have a stone, and this stone will have a certain weight. So that's the force from the gravity. So let's say the weight of this stone is 10 newtons. So that's the magnitude. And we know that gravity always points downwards. So the direction is down. So we say that this vector has a magnitude of 10 newtons and direction is downwards. So that's how we would represent this. Right, so that's how we would describe these real life examples of vectors. Now in mathematics, in order to help us use these vectors for calculations, what we would often do is that we would use some notations to represent these vectors. So for example, if I look at this displacement vector, I might think about it as this arrow, which has a certain length and direction, and I might call the two ends of the arrow A and B. Right? So I think of a line in a certain direction towards the east, and I call the two ends A and B, and I can represent that length by calling it AB. So that's how we would represent a line in mathematics or in geometry. Now, but because this line has a direction, the way to show that is to draw a little arrow on top of AB. So if you see this notation AB with an arrow on top, what it means is that it is a vector whose magnitude is the distance from A to B, and the direction is pointing from A to B. So that's what this notation would mean. Now there is another way to other ways to represent this vector. I can simply call this whole arrow, I can simply represent it by say a symbol like little a, for example. Now if you look at textbooks in mathematics, you will often see that if I use a single letter to represent, if they use a single letter to represent a vector, that letter will be printed in bold, meaning that you have a very thick font on the page. It will look something like that. Now, but to write this in your calculations, to represent this in writing, it would be quite troublesome to scribble over it to make it look thick. So there are a few ways to represent a letter which is a vector. One way is to use the same arrow, so I can do A with an arrow on top. That's one way you can write it. You see this in books as well. Another way I can write it is I can write A with a squiggle at the bottom. Now I am more familiar with this notation, A with a squiggle at the bottom. So I'll use this in this session. But you can use A with an arrow on top as well. No problem. Okay. Next, we are going to look at the idea of adding two vectors. When we add two vectors together, the answer is called a resultant vector. Now, but how do we add two vectors? We know how to add two numbers, like 1 plus 2 is equal to 3. That's easy because numbers are just numbers. Numbers have no directions. But vectors have directions. Vectors have magnitude and direction as well. We might be able to add the magnitude, but how do we add directions? So to understand what to do, let's look at the displacement example again. Suppose that a person walks to the east. Look at that person again for 100 meters. So that's one vector. Now, suppose that she then turns and go northeast that way for another 50 meters. So what does it mean by the resultant, or what does it mean by adding those two vectors? Now in this case there's an obvious meaning, which is that if we go this way by 100 meters and northeast by 50 meters, it would end up effectively going that way by a certain distance. So we can think of this straight direction from his starting point to the final point as the resultant vector, because he would end up in the same place if he go straight instead of going 100 meters east and 50 meters northeast. So this distance and direction is therefore the resultant of those two vectors. Now looking at this actually gives us a simple way to add two vectors. All you need is to put the two vectors, put the head of one vector to the tail of the other vector, and then draw a straight line joining one end to the other. You have a triangle. Alright, and this new side of that triangle gives us the resultant. But how would we describe this resultant vector? We know that to describe a vector, we have to know the magnitude and the direction. So to describe this resultant vector, I would need to know the distance for the magnitude, and I would need to know what direction it is in. Okay. So just very briefly to give you an idea, we know that this is towards northeast, so that means that this angle here is 45 degrees. Alright, and that means that that angle in the triangle is 135 degrees. So we have a triangle here and we know the two sides and one angle. So there are two ways to find this distance and direction. To find this distance, we can do it by a construction or a scale drawing. You can just take out a ruler and a protractor and imagine that you want to say use a scale of say 1 cm to 10 meters. Right, so for example you would represent the 100 meters by 10 centimeters and the 50 meter by 5 centimeters. Okay, so take out your ruler and protractor and draw 10 cm there, 5 cm there, measure out the 45-degree angle, and then join the two corners of the triangle and use your ruler again to measure this new distance, and that will give you the distance. And then you can take the protractor out and measure that angle there in your drawing, and that will give you the angle to the east. Or you can also work out the angle to the north to get a bearing. So we can do it by drawing if we really want to find this vector, to find the distance and the direction. Or if you have looked at my explanations about trigonometry on sines and cosines, you will also know that you can use the sine and cosine rules. In this case, because we know the two sides of the triangle and the angle in between. You can use the cosine rule to find the third side. So that gives you the distance using the cosine rule. And after that, you can then use the sine rule to find this angle. So sine rule and cosine rule gives you the answer. So two ways to do it, either by drawing or by trigonometry. Alright, let's move on from there. So this is called the triangle law of addition. Let's look at another example. Right, we do not always get such an obvious examples for our calculations. So sometimes, for example, you might get a question like that. Say, you get a straight line there, okay, and you're given a vector in this direction and one in this direction. Let's say that's 4. The length of that is 4 units and the length of that is 5 units. You might be given, say, an angle there of 60 degrees, angle there of 40 degrees. Alright. And the question here again is to add the two vectors. So I have these two vectors. Right, the question does not really say whether it is a displacement or a force or what it is. It doesn't really matter, because the idea is that we can use the same idea as before using the triangle law of addition to add those two vectors, right, in just the same way that we added displacement. So you can always imagine that these are displacements, but they're not quite displacements, because you have two arrows that seems to just go in different directions. So the way to add these two vectors would be to imagine that these are actual arrows pointing in the different directions. So imagine that you actually have two arrows that you can move around. Okay, so you have this arrow there. Imagine that you can just move it around. So suppose that I take that out and put it down here. Okay, so now I would have this arrow there, distance 5. Okay, and I must remember that the angle must remain 60 degrees to the vertical. Alright, so even though I can imagine moving it around, I must make sure that I keep the direction and the distance fixed. Now, let's look at the other arrow. So I'm going to take this arrow out as well, and I'm going to move it around. Now I'm going to move it so that the tail of this arrow touches the tip of the other arrow, like that. So I've moved this over to there. Right. Again, I must keep the distance and the direction of 40 degrees to the vertical, so that's the vertical here. I must make sure that that's still 40 degrees. So now I have arranged it in a similar way to the last example when I talked about displacement. It's like a man walking 5 meters in that direction and then 4 meters in that direction. So what is the resultant vector? Well, I will just join the starting point here to the final point. So you join the tail of the first arrow to the tip of the second arrow. So that's the resultant. This line, the length of this arrow gives you the magnitude and the direction gives you the direction of the resultant vector, the resultant of adding those two. So once again, in order to find the answer, we must find the length and we must find the direction. So for the length, you can do it by drawing, like I described just now. Just take out your ruler and your compass, measure out this distance and the angles, draw the triangle, and then you can simply use your ruler to measure that distance. Okay, that's a simple way. And as to the direction, if I want to know the direction of this arrow, now you have a choice. The idea is that to describe the direction of an arrow on paper or on the board, we usually refer it to some direction. For example, in this case, we can refer to the vertical direction. So if I refer to the vertical direction, I can, for example, use this angle. Okay. So if I can find that angle, then I can describe the direction. I can just say that this resultant vector is so many degrees, and I can take out my compass to measure that angle. It's so many degrees to the vertical direction, or to the upward direction. Okay, or I can also measure that angle if you like, and say that the resultant vector is so many degrees to the downward vertical direction. So that's doing it by drawing. Right, let's move on to look at some other ideas that will help us to do more calculations with vectors. Now that's the idea of equal vectors. Suppose we have two vectors. So vector AB and vector PQ. So they look like two different vectors, like two different arrows in different places. Now, but suppose that these two vectors have the same magnitude, so same length of the arrow, and suppose that they are pointing, that they are parallel, right? That they are pointing in the same direction. Now, as I said just now, a vector is described by its magnitude and its direction. So if I have two arrows, two vectors like that, even though they are at different places, as long as they have the same direction and the same magnitude, we say that they are equal. We say that they are the same vectors. So I would say that if I represent this vector by AB with the arrow on top, and that vector by PQ, the arrow on top, I would say that they are equal. Now you might find that a little strange to say that those two vectors are equal, because obviously they are different arrows, right? Now, the reason why it is okay to say that they are equal is not because we are saying that that arrow and that arrow are the same arrow. Of course, they are different arrows, but we are saying simply that the length of those two arrows and the directions are the same. And that's what vector means. Vector just means the length and the direction. So it's like if you have, say, two persons of the same height, so me and my friend, if you have the same height, if say both of us are 160 centimeters tall, so our heights are equal, alright? We are not the same person, okay? I am a different person from my friend here, but we have the same height. So it is our height that is equal, but of course we are different persons. So the height for me is 160 centimeters. For him it's 160 centimeters. So both are equal to 160 centimeters. So in the same way, if I have these two arrows there, or those two vectors, those two arrows, they are different arrows, but we say that they are the same vectors. So think about vectors like you think about height or money or weight. It's just a quantity that describes the size and the direction of the arrows. Okay, A, B equals to P, Q. Now just to get used to the way that we write down these notations, let me also write it down in the other common way, which is to represent the whole vector by a single letter. Let me call that B with a squiggle at the bottom. Call that Q with a squiggle at the bottom. So if they are the same vectors, I can also write V is equal to Q. So that's that. Right, next, I'm going to talk about the idea of negative vectors. Now we know what negative numbers are. If you have the number 2, for example, you can talk about -2. That's a negative number. And you can imagine drawing -2 on a number line. For example, I have a number line there. That's 0. That's 2. -2 would be on the other side of 0. So that sort of gives us the idea of a negative vector. On a number line, the -2, the negative number, is as if it's on the other side of 0, right? So that's the negative side, that's the positive side. So there is this idea of direction when we talk about positive or negative numbers. So in the same way, imagine that I have this vector, that AB, this direction, right? Now imagine that I have this vector here with the same distance AB, but pointing in the opposite direction. Now I should give it a different name. PQ. Alright, imagine that I have this vector here with the same magnitude but in different directions. Now this vector is AB, that vector is QP, pointing from Q to P. So they're not equal. Now, we've just looked at equal vectors, and equal vectors means that they must have the same magnitude and direction. But in this case, although they have the same magnitude, they have opposite directions. They are even parallel to each other. Okay, but they are pointing in the opposite direction. So in this case, we can think about QP as and AB as related by a negative sign. I can say that minus of QB is the same as AB. And the idea is that I use the minus sign to refer, to mean that I reverse the direction of QP. So if QP points from Q to P, then minus QP points from P to Q. So putting a minus sign in front of the symbol for the vector will have the effect of reversing the direction of that vector. Reversing the direction, but keeping the same magnitude. So it's as if you just take this arrow and flip it the other way around. So that's what it means when if we see a minus sign in front of a vector. It just means the reverse direction. Okay, but it's still parallel. It's still along the same line. Right, that's now I'm going to go back a little bit to the idea of resultant vectors again, the idea of adding two vectors. Now I have talked about how to add two vectors using the triangle law of addition. Now there is another way to think about how to add two vectors. Now let's have a look at, say, this vector and this vector. If I call this vector A and this vector B, I've drawn this vector so that they are end to end. Alright, so that the ends are touching each other. Now I've explained how to use the triangle law to add the two vectors. I have to take out one of this vector and move it until its tail touches the tip of the other vector. Now, but there is another way to do it when they are actually end to end. And the way to do it is to draw a parallelogram. So this is what I would do. I would imagine that the two vectors are the sides of two sides of a parallelogram, and I'll complete the parallelogram by drawing the other two sides. And then I would draw a diagonal from the tail to the opposite corner. And this diagonal gives the resultant. So this would be the A plus B. Resultant vector. Now we can actually see that it is related. In fact, it will give the same answer if we use the triangle law of addition, simply because this new side there is has exactly the same magnitude and direction as B. So that means this side is also equal to B. So if you look at this A and this B, what you actually have here is a vector B with its tail joined to the tip of the vector A. And this diagonal here simply joins the tail end of A to the tip of this B there, which is exactly the way that we did it for the triangle law of addition. But this is just another way of doing it, just by looking at these two vectors when they're joined tail to tail. We can complete a parallelogram and find the answer by drawing this diagonal. So sometimes this way of doing it is more convenient. Right, a lot about vectors is a lot of things about vectors is about how to get used to notations and how to use these notations to do some mathematics. Now let's start with this example. Now in this example, we have a parallelogram. That's a, right. Those two sides are parallel and those two sides are parallel. Now the corners are labeled as A, B, C, and D. And we want to think about this line pointing from A to B as a vector, which I call P. And this line from B to C as a vector, which I call Q. Okay, the first thing we want to do is to express the vector DC in terms of P. Then I want to express vector AD in terms of Q, and the vector AC in terms of P and Q. So these are what we want to do. We look at these three parts of the question. So express DC, right? DC is this vector here. That's DC. I want to express it in terms of P. Now if you look at the vector DC and the vector P, you see that they have the same direction and they have the same length. Now if two vectors have the same direction and the same length, they are equal. So therefore, DC is equal to P. So if I call, let me give these different parts of the question some numbers. So if I call it question 1, question 2 and question 3, so that's the answer for question 1. DC equals to P. That's quite simple. Now next, let's look at AD in terms of Q. AD is here. And Q is the vector down there. And once again, you see that AD and Q have the same length because they are opposite sides of a parallelogram. And they are pointing in the same direction as well. So AD is equal to Q. That's simple enough for the first two. Now how about AC? I need to express AC, which is this vector here, in terms of P and Q. Right. P is there, Q is there, and AC is here. So if you remember the triangle law of addition that I described just now, if I add the vector P to the vector Q, I can do it by joining the tip of P to the tail end of Q and then joining the end of P to the tip of Q to form a triangle. And this is exactly what we have already. Right? We have the triangle drawn for us right here. So therefore, AC is simply the vector P plus the vector Q. And that's the answer. I've just expressed AC in terms of P and Q. So that's how we do this question. So if you're seeing this for the first time, it would all seem a little abstract, but the main thing is to remember that a vector is simply something that tells you the magnitude and the direction. So magnitude, if it helps, think about it as an arrow, and magnitude would be the length of that arrow. So we are simply, if you're comparing two different things, alright, like two different arrows, then what you need to compare is the length of the arrow and the direction of the two arrows. And if the lengths and directions are both the same, then the vectors are the same. Right, next we are going to look at subtraction of vectors. So suppose I have two vectors. Vector A, vector B. Now suppose that I want to subtract them this time. Now we have seen how to add vectors. What does it mean when we want to subtract vectors? So what I want to do is I want to find A minus B. Now when we looked at adding two vectors, we have seen that when you add one vector to another vector, you get a resultant vector, which is the answer basically. So the resultant vector, when you add two vectors, you can get a resultant vector. So when you subtract two vectors, you can also get a resultant vector, which means that's just another way of saying that when you do A minus B, when you subtract the two vectors, your answer should be a vector, and the problem is to find this vector. Alright. So first let's look at what this means. A minus B. Now the way to do it is to relate this to what we have learned just now. So what I'm going to do is to say that A minus B is the same as A plus the negative of B. Now we have learned what negative of a vector is. We have also learned how to add two vectors. So it's time to put the 2 and 2 together to find out how to subtract two vectors. So let's look at that. Let's see what we can do with it. So first of all, let's look at the minus B. Now B is there, and minus B just means a vector that is pointing in the opposite direction but has the same magnitude as B. Right, that's minus B. Now, so minus B is itself a vector, just pointing in the opposite direction to B, and I have to add that to A, meaning that I must add this vector to that vector now. Now we know how to add vectors. If I have that vector and that vector, we can do it by moving these two vectors around. Remember that when you move the vector, you must keep the same direction. So let me move this minus B over there. Okay, so I must keep the same distance and direction. That looks a little bit wrong. Something like that. And then I must move this other vector so that the tail of this vector touches the tip of the other vector. That's the A. Okay, and then I must join the tail end to the tip to form a triangle. That's the answer. That would be A plus minus B. which is also the same as a minus b. So this has just given us a way to find the resultant of a minus b. It's just that. Right. Now it's a little bit troublesome still to have to think about first changing it to the minus to the addition of a negative vector, and then to reverse the vector, and then to move things around until we get the triangle. So in order to shortcut this, all these steps, what we could do is this. Let's start from those two vectors. Now what I'm going to do is, I'm simply going to move those two vectors, say move one vector until the tail end touches the tail end of the other vector. So in other words, I'm just going to draw B there. Okay. And I'm going to move A here. Just going to draw them end to end. Right. Now if you look at this and this, you see that they are just this side and this side of the triangle. So all we really need is to find the third side of this triangle. And if you look at this arrow that I've just drawn, it is pointing from B to A. Like that. So that's A minus B. So that's how we can get the answer quickly. If I need to do A minus B, I simply move A and B until they are end to end, the ends touch each other, and then I draw an arrow from the tip of B to the tip of A. So this triangle gives me the answer. It gives me the A minus B. So now I have a triangle law of subtraction for vectors. Now how do I know whether I should draw the arrow from B to A or from A to B without having to work through all that? But the way is to look at what you're subtracting. If you are doing A minus B, okay, then you would always draw the arrow from the B to the A. You draw the arrow from the subtracted from the second vector to the first vector in your subtraction. Alright, so it goes from B to A. So that's how we can do subtraction of vectors on a picture. Okay. Okay, let's look at one more thing. Multiplying by scalar. Now, scalar just means a number that has no direction. So if you are confused by this term, just think about it as a simple number. Okay, number only, no directions. So this is about multiplying a vector by a number. Now we have looked at adding vectors, we have looked at negative vectors. Well, what does it mean by multiplying a vector by a number? So let's look at this example. Suppose I have this vector, I call that A. Right. Now if I multiply A by 2, for example. 2 times the vector A. What does that mean? We know what minus A means. Minus A means the same vector but in the reverse direction, right? So 2 times the vector A actually means a vector in the same direction but twice as long. That's what it means. So once we have this idea, once we understand this idea, you can think of any number times A times the vector. So 3A, for example, would be a vector in the same direction but 3 times longer. And I can also talk about half A. Half A would be a vector which is in the same direction but half as long. Okay. What about minus? Well, we know what's minus A, but what about minus half A? Well, so minus half A would be a vector in the opposite direction because of the minus sign, opposite direction of A, but it will be half as long because of the half. So that's minus half A. So now we know what is meant by multiplying by a scalar. Alright, when we multiply a vector by a number, we simply have a new vector that goes in the same direction, but it becomes longer by that number of times. And if that number happens to be a negative number, we have to flip the direction as well. But it must remain parallel to the original vector, except that the direction becomes opposite. Now, following from this idea here is the idea of parallel vectors. So let me clear this first. We have seen just now that when you multiply a vector by a scalar, the answer must be a vector that has the same direction but maybe a different length. Now let us now start by looking at two vectors that are parallel or that are in the same direction. So if they are in the same direction from what we have just learned, we know that it must be possible to think about this longer vector as a number times A. Okay, some number times A. Now, if let's say I don't know what that number is, I can call it H, as in algebra. Alright, the letter H, it represents a number that I don't know, and I let this vector be the H times the vector A. So I'm doing some algebra down here. So if I know that this vector has the same direction as A and it has a different length, some length that I don't know, then I can call it H times A. Now let's turn this around. Suppose that I have a different, another vector here. Suppose that I don't know whether this vector has the same direction as A. I don't know whether or not it's parallel. But I'm told that this vector is equal to h times a, is equal to a scalar times the vector a. So this information is enough to tell me that this vector is actually parallel to the vector a, because it is only possible to have, because h times a, alright, is just a scalar times a, so that's why it must always be a vector along the same direction but with a different length. So that's how we understand, that's what we have understood from when we learn about scalar times a vector. So as long as you see this expression h times the vector a, this vector is always perpendicular, is always parallel to the vector a. Okay, so we will stop here for this session. See you next time.